All right, we'll get started. Good morning. Everybody hear me all right? Fantastic. The one guy in the back with the thumbs up. This talk is digital twins and space, digital twins for space, great start on the title slide, and critical infrastructure defense. We're going to talk about rehearsing failures safely and early using simulators. I'm Cody Cutright. With me today I have Donovan Ice. A little bit about us. Donovan, waving up front, says he is an adult. He wants everybody to know that. I didn't put that in there. We both are systems engineers for TMC Technologies. I'm from McCannon. Donovan's from Clarksburg. I got my bachelor's in math and computer science from West Virginia Wesleyan College and master's of engineering, electrical engineering from West Virginia University. A little fun fact about me, I've backpacked over 5,000 miles. Donovan's from Clarksburg, West Virginia, and got his bachelor's in cybersecurity from West Virginia University. So we both work for TMC Technologies. TMC is located in the Whitehall, Fairmont area of West Virginia. Broadly speaking, as a company, we're experts in software-only simulation of hardware and experts in hardware emulation. So the goal is that we can actually take flight software that's made to run on a satellite, and we will run it unmodified on a computer. So the software does not know it's not actually running on orbit. This lets us do some very unique and challenging and otherwise very difficult to do test cases. If you only have one of a satellite, they're not going to let you test something on it that might break it, right? So this is a way to get around that. Virtual test beds also let the development proceed without immediate access to a flat sat, and we're going to cover some of these more in depth. But long story short, if there's 20 of you, we don't have to have 20 hardware strings. You can do most of your development on a close enough high fidelity digital simulator, and then you can vie or schedule that flat sat time for the real run for record. You're not just trying to run it on the hardware over and over. And also we find that by doing this, we shorten development timelines. So what we're accomplishing, the photo up here is the James Webb Space Telescope. And what we accomplish with high fidelity simulators like this is we take the flight software that actually runs on orbit, we take the physics, everything including solar wind, pressure, avionics, the actual flight boards. We shrink all that down and you can run it on a laptop. Sometimes we can do it in cloud deployments as well. And laptop, your mileage may vary. If you're doing a really complicated sim at a very high fidelity, it might not be super fast. But generally speaking, in the example we're doing today, we're going to run it two times real speed. So even if you just think about long duration testing and things of that nature, if you have a requirement for 30-day long duration must run unmanned, you can do that in 15 days. You can do that in 7.5 days, depending on the computer you have and how fast you can run. So really cool use cases for what we're getting into. So this talk really marries sort of satellites, embedded systems, digital twins, and kind of just like this big circle of everything that's happening. But an embedded system, more or less, I don't know that there's really a single formal definition. It's a little vague. But it's a specialized computer system with dedicated functions, and it has a processor, memory, and I/O. So specialized is really the key word. It's not a general purpose computer like your PC or your laptop, or even your phone has a lot of functions outside of just being a phone. It's generally purpose built, and it has little or no human interaction. And we generally expect these things to run for a really long time on their own. So more or less bomb-proof, hazard-proof, fail-safe. Embedded system operations, as we keep doing this background here, they really work on a stimulus and response. Something comes in, the system reacts. A lot of these are considered real-time systems, immediate, and it gathers the data, prioritizes it, and reacts accordingly. We talked about the long-term deployment. Sometimes that's expected, sometimes it just happens. Sometimes things get deployed and they get left, right? You hope that it's stable. And the complexity varies. A lot of people have seen sump pumps in a basement. You could have the industrial equivalent of a sump pump. Just water level gets high, it turns on. Maybe it's an analog system. Maybe there's a small embedded microcontroller, though, that's actually powering that. So it varies. It may be as complex as something as the Hubble telescope, which is still up there. Generally speaking, it does its own thing. It did have a few servicing missions, which was really cool, but it's deployed and more or less it's just left up there. So we have to balance these things. We talk about, we've already said the word microcontroller. I've given a little bit of it away, right? We got a few things. Size. Size is important for embedded systems. If they were big, you couldn't embed them. If you had to embed a refrigerator into your smartphone, you wouldn't want to carry it around, right? It's a little too big. Not only is it too big, it would weigh too much. A lot of these embedded systems are in embedded systems, so like larger, more complicated. A car is a good example. You have a lot of embedded systems within the vehicle itself. Even the gas pedal on a lot of newer vehicles is an embedded system if you think about it, right? It's not directly linked to the fuel that goes into the engine. It's actually by wire, right? So, and there have been recalls actually of those failing. So that's an example of an embedded system that maybe has had some issues. Other considerations, this is all together considered SWaP-C, size, weight, and power cost. Power is very important. If embedded systems are power hungry, they can't run for long times on battery backup. And generally, because they're resource and power constrained, they're very limited in the number of things that they can do. And then cost. If microcontrollers weren't cheap, we couldn't use them in everything. So let's do a couple examples, make sure we're kind of on the same page. PLCs. PLCs are industrial level programmable logic controllers. There's a lot of ways you can look at the PLC itself as its own embedded system. It's got a couple buttons, you can interact with it, but once it's set up, it does all of its automation on its own. You can also plug that into a larger system and think of that itself as an embedded system, the I/O from external stimulus into the PLCs. A lot of times, something analogous to that is traffic lights. We expect traffic lights to more or less just work. We've all seen the flashing red ones out of service, but you know, there's a small microcontroller. Humans don't typically, unless you're using a crosswalk, directly interact with them, and they're deployed and expected to work. When you pull up, the light senses you, it changes green, you go through. And then a lot of home appliances are really embedded systems. We talk about Internet of Things. I don't know why washers have Wi-Fi. I truly don't, but they do. Bluetooth, Wi-Fi. You know, I don't know what's going on. I just want my clothes washed. But there are several microcontrollers in a lot of these, and I think that's how they sell you more when they break. So we've covered a little bit about embedded systems. Let's talk about the overlapping qualities of satellites, critical infrastructure, and embedded systems. And we'll start taking this a little more space-focused. Obviously, they're specialized. They're limited in flexibility. I can't play solitaire on a satellite. Well, maybe I could, but that'd be about all you would accomplish, right? There's not enough processing power to really like draw screens, for instance, and do all these things. They don't have the visual output because they're not specialized for that. They don't have a dedicated graphics card. They're limited in processing power. They're limited in storage. Pretty much any cell phone you have has a lot more storage than not just embedded systems, but surprisingly a lot of satellites, unless they have a dedicated storage controller that's a lot of money. They're dependable, they're predictable, and they're bare bones. They don't have a lot of overhead and tools that let you interact with them. A little screenshot here. This is Voyager 2. Now, according to the great Google, if you want to believe it, I don't know, it is considered the longest running embedded system, the computer system on Voyager 2, at over 40 years. I just think that's the longest we know about. There's something out there still taken away in a basement somewhere, or a firmware on a router or something that somehow is on backup power, but it's cited as a pretty common example of long-term embedded. If the command handler goes down, we're in pretty bad shape there. So let's look at some overlaps and some differences in satellite and critical infrastructure. Got to have Venn diagrams at some point. Satellites need space. That seems kind of obvious. That's pretty much the definition. It's an embedded system in space. Critical infrastructure is rarely checked on, whether that be by design or necessity. You think about like water dosing meters. Sometimes they're just deployed, and some guy's out here and he just This tank needs more chemicals to treat the water, and he puts it in, and it should be audited. Maybe it is, maybe it isn't. Stoplights are another good example. Nobody really checks on them, generally speaking, unless something goes wrong, right? That's when we check on embedded systems. When they stop working, somebody says, I should check this thing a little more often. Satellites, by contrast, are checked on pretty regularly. Otherwise, you wouldn't get data out of them. They're embedded. They're hard to touch. And there's really some overlap here with feral cats, which isn't really the point of the talk. But feral cats need space. They're hard to touch, and they're rarely checked on. So I had to find something that was the third thing. So now let's get more technical. PLC model S315-2 and S7417. Do those numbers mean anything to anyone? Cool. Awesome. Those are programmable logic controllers targeted by the Stuxnet virus. It was uncovered in 2010. It crawled across numerous air-gapped networks searching for PLCs in Iranian centrifuges. Think about that for a minute. Numerous air-gapped networks looking for Iranian centrifuges. It lay dormant on the computers it infected. It recorded their PLC output. It wrote malicious code and rootkits to these PLCs, and then it intercepted user commands. If you don't know anything about PLCs and SCADA, you're pretty much a supervisory control and data acquisition. There's usually a human-machine interface, an operator terminal that you can run this stuff off of. And you take it as basically the word that if it tells you the blinky light is on remotely, you believe it that the blinky light is on. That's not what happened with Stuxnet. It actually played back recorded output. So when you commanded it to do Series A or whatever segment of code, command sequence, it would say you're doing command sequence A. It played back all the telemetry, the speeds, the rate, the cadence, the housekeeping. It updated the current times and the telemetry points. But none of that was real. So whether or not they knew it, they had, which they didn't, they had lost control of their own centrifuges. The only thing that the enrichment facility in Natanz did notice is they were replacing a lot of centrifuges. And nobody knew why. Because at the time they still had, I'm probably going to butcher the wrong acronym, but the UN was coming in, they were doing inspections, and the UN inspectors were like, you guys are going through a lot of centrifuges, what's going on here? And they're like, I don't know. Beats me, right? So how did they find this thing? Because it was not the enrichment facility that found Stuxnet. They certainly saw the side effects of it, but somewhere in Belarus, I think it was Minsk, a computer was stuck in a reboot loop. It just happened to have the same supervisory control software installed on it, but it was not in Iran. And basically a variant of Stuxnet found the computer, and it had a bug. This is why you test your software before you ship it. And the computer got stuck in a reboot loop, and they couldn't figure it out, but it was just aggravating enough that they called somebody and said, please come look at this. So they came in, and the company in Belarus said, I don't know what this is. I've never seen this before. This looks bad. It looks complicated, and that's what unfolded and found Stuxnet. Stuxnet itself, just in the exploits used, is worth millions of dollars. Previously undisclosed zero-day vulnerabilities all chained together to let this virus replicate itself in a computer, look for control software. If it wasn't there, it just replicated to every USB it could find and went on its merry way, and then deleted itself off the computer. So that tells you that it was nation-state sponsored. It is the first recognized cyber attack to destroy key infrastructure, physically destroyed. So with all that in mind, are embedded systems safe? How do we know? You know what I mean? If it's telling you, if you're thinking of it as an embedded box and you look at it and you say, hey, how hot is it outside? And it says 32 degrees. You say, fantastic. You step outside and it's 98. You're like, I don't know about that. Like at what point do you stop trusting it, or do you begin trusting it? Well, if we take that and we expand it to traditional computer networks and systems, how do we know what to protect our systems against? There are white papers and we get notifications, but if you're doing security research or you're wanting to really harden a system, MITRE publishes an attack framework, and I don't remember how many, there's like 14 tactics with I don't know how many techniques here, right? But this is open, anybody can go look at it, and basically just says this is how adversaries may think about compromising your networks, your systems. And maybe Iran could learn something from this, I'm not sure. Air gapping, which used to be the gold standard, right? And if you've never done an ATO, it's an authority to operate for a computer network, and they come in and they're like, what's your security policy? How do you fix this? And everybody says, it's air gapped. Nothing touches it. Not true. Things get plugged into it. But this doesn't really apply to embedded systems and get at the root of what we're talking about with digital twins. So we need to know how and what to protect our embedded systems against. How do we do that? Because our adversaries have questions. Whoever wrote Stuxnet had questions. If you have a satellite up there that nobody knows what it does, somebody wants to know what it does. And our adversaries want to know what's in the box. How do we get to it? How does it tick? How do we adjust the input? How do we cause it to crash? How do we get it into a mode where we can manipulate it further? A really good example of what they may be trying to accomplish is a lot of satellites have a safe mode. And in safe mode, the satellite says, something's wrong, I need help. Historically, what that means is, I'm turning off all of my encryption. The first person to talk to me can tell me what to do to fix this problem. Something's broken. So if you can get something into a failure state, a lot of times you can get that safe mode unlocked. People are getting better about that. That's not so much the case anymore, but like it's a real thing. So, Aerospace Corporation released Sparta. Now this is space focused, however, we've covered the overlap between space and a lot of embedded systems. So it's the Space Attack Research and Tactic Analysis tool. It's got 87 different techniques and counting. They add them as they come up with something viable where people submit really good suggestions. And you can click through these techniques and it'll walk you through the basics of what you're trying to accomplish, how somebody would do it. So if you're looking for things to throw at embedded systems, this is a great place to start. But how do we test this? If you have all these, what is it, 87 things you need to like test against, how do you do this? How do you have the time to even start thinking about this? Your boss is not going to let you test on the only copy of something you have. If you're like, listen, this could happen. It's like a 1 in a million chance. But if somebody flips this switch somehow, it's going to break. They're not going to let you do that for real, right? And the answer to doing that is digital twins. So digital twins, we use them a lot of work, obviously. We make a lot of them, but they shift the traditional software development lifecycle, and it greatly increases at the same time your test resources and opportunities. So if we look on the left here, in a traditional flow, you start with hardware. Somebody that is very important and makes way more money than probably most of us comes up with a list of requirements of what your system's going to do. And they say, the system shall do science in space. You're like, cool, what science, right? And it feeds down into more. The science shall be this and it shall be that. And eventually this translates into a list of hardware that you need to build your satellite. So you go to the manufacturer and you say, I want to buy this hardware. And they say, that's awesome. It's $300,000 now, and you get it in 18 months. And you're like, cool, what am I supposed to do? Well, you wait 18 months in that scenario. Once you have the hardware, you can start checking it out with software, because you can't do anything in the meantime. Once you hit a critical mass on software, now you can start to integrate and test your hardware. So you can see where this is like a drawn-out process. This is really long. Once you're making duplicates of something, it's not a big deal, but for a lot of science missions and one-offs, this takes forever. Digital twins fix a lot of those problems. As soon as you know what hardware you're ordering, you can get the specification sheet, and it says, when you write to register 5, blinky light number 1 turns on. And you're like, that's really cool. And if you have the spec sheet and you have the registers and the expected behavior, you can start coding that up in a simulator. So as you start to receive hardware, you're already writing the software for it. You already have some level of fidelity to your simulator. It might not need to be high level. It might be a black box that you say, I wrote a 1 to register 5, and it just tells you blinky light number 1 is on. It doesn't have to be super high fidelity depending on what you're testing, but it gets you off the ground to start your core development. And then as you do that, you have more time with your hardware and your software once it starts to arrive. You can start integration and testing earlier because you can work out the kinks of integrating your simulators and how that fits into your development framework or your flight software framework. And overall, what you get is you get a higher product quality, reduced time to market overall, reduced resources cost, because now this entire room of people, everybody can have their own laptop and develop their own software or their operations procedures. And then we can just test it on the hardware when we finally have the hardware. So there are a lot of disciplines that can benefit from this. Developers, early development opportunity before hardware arrives. INT, you can do end-to-end testing early. We're going to walk through a sim later that has ground software all the way up to a satellite and comes all the way back down. It's a closed loop with dynamics. Operations, operators can dry run scenarios. You can do day-in-the-life testing. You can also train your operators in failure modes. If this little error message comes down, this thing is probably broken. How do you treat it? How do you work with it? We talked about increased test resources. You can do dynamic testing. You can do exploratory testing. You can set values to things they should never, ever be in the real world and see what happens. You can train all of your new personnel, new guys, interns, people you just want to keep busy while you do something else for a little while. You can give them a box and say, go play with this. We can do, like we said, hardware modeling and fault injection. And then researchers, we're going to integrate and demonstrate new technologies, maybe do security research. We're going to see an example of that here shortly. But the goal of digital twins, not only to shorten everything else, is you want to break the copy, not the asset. You don't want to go to your boss and tell him that you tested the self-destruct sequence on the simulator, and your boss says, we don't have a simulator. Right? That's not the scenario you want to be in. Yeah. And it's hard to tell, but I'm sure there have been similar issues. So let's look at a real example. This happened. I'm going to feel old saying this. I interned on this project. Simulation to Flight 1, West Virginia's first satellite. We built it here in West Virginia. We assembled it in Fairmont. We did the testing in Fairmont. We wrote the code, TMC Technologies, as a contractor for NASA. And we partnered with West Virginia University. They provided some of the science payloads. And we also leveraged some existing NASA Goddard efforts. The end result was a CubeSat about the size of a loaf of bread, more or less. And we used this to demonstrate the digital twin capabilities. We built the simulator as part of our research effort to prove that you could have a simulator and use it on hardware. And what resulted was an open source solution that anybody can use, and it's the NOSCube platform. It started as a framework. It just started as, you can use this to build certain things. Since then, we've actually turned it into a design reference mission. It's an entire satellite in a box. You can download it. You can go play with it. It has attitude determination control, solar panels, batteries that charge and discharge, star trackers, sun sensors, a whole bunch of stuff. It launched on Alana 19. I would love to tell you what that acronym means. It's educational launch and a bunch of things I don't remember. And 5 years later, roughly in 2024, deorbited. So for a 3U CubeSat, from part of a team that had never really built the hardware before, a lot of us work on space things, but we do a lot of software, successful, gigabytes of data, and it's all down at WVU. So pretty cool. We did it all with NOSCube. We get a little screenshot of NOSCube there running in the background. And then some of the hardware on the board as they do some integration and testing procedures. As I've said, NOSCube, not github.com/NASA/NOSCube. Go download it and play with it if you have some time. Please do. It's got a small but growing community of invested people who are using it for all sorts of really cool things. What was that university that just published a paper? New Mexico University, New Mexico just published a paper on some proof of concept cyber scenarios they did with it. So that's just the one I know about off the top of my head. There's a lot of other things going on. But it's open source, virtual, all digital flat sat. Been around, I'm starting to feel older, since 2016. It is maintained by TMC Technologies. We still maintain it. We also have a commercial version with the support called SmallSat Digital Twin, and we can also integrate hardware with that as well in a product we call FlexSat. We have several universities that are using FlexSat. So if you need hardware in the loop for something and you're doing a satellite sim, we can do that. But the benefits have been proven across multiple missions. We started with STF-1 like we talked about, and now it provides a baseline for mission development out of the box. So just run down a quick list of the missions. We've got STF-1 launched and deorbited, Burst Cube has launched and deorbited, Snoopy launched and deorbited, Petite Sat, honestly don't remember off the top of my head. Dione is wrapping up development. GTO Sat is developed, it's in a box charging, waiting for a ride. And then LIMS is in active development. So LIMS is the oddball in that it's the only one that's not a satellite because it's being placed by astronauts on the moon. But all of these have used NOS Cube for their development. So it's got a lot of heritage. It's pretty cool. It's worth checking out. A little bit about the architecture because we need to understand it going forward for the demo. It's a combination of multiple pieces of open source software. We have Dynamics from a product called 42, which is from NASA Goddard. Eric Stoneking writes that. And it's a virtual spacecraft that has multiple software options. It says core flight software. This is a little bit of an older image. We also have F prime as an option. We have various simulators, hardware simulators that are running. We also have ground software in the loop. And then we have the NOS server that ties it all together. So that is, in a nutshell, what it is. It also supports several ground stations, or you could put your own in it if you would like to. AIT, Cosmos, OpenC3, and YAMS. And two flight softwares, Core Flight System and F prime. A really quick glimpse. There's a lot of things going on here. Don't let this overwhelm you. In the top left, we've got the hardware models running. In the top center is flight software. That's the console that prints out events that are happening. In the top right, we have our time driver. Bottom left, we have the dynamics. That's the eye candy. People love to see the dynamics because you can see the satellite react. If you spin up the reaction wheels, it'll turn, it'll point. You can see where it is in the map over the Earth. So really cool to have the dynamics in there. It really helps the thought process. And then in the bottom right, we have the ground software. So let's do a simple space mission here. What we're going to design is we're going to measure air moisture over the United States. That's our goal. That's our top level. Do science over the United States. We will further define that as the United States. We're just going to call this continental United States, Alaska, and Hawaii. So knowing all that, we have a stimulus. The stimulus is where we are, right? That's our GPS coordinates. And then we have a desired response based off those GPS coordinates for our embedded system. It's really just turn on the instrument. Everything else we can figure out later. So basically, if we go back here, got a picture of the Earth. It's kind of hard to picture drawing a box on. But if you would flatten it, you can define your stimulus ranges just as numbers. You can see what these boxes look like. So if this is a map of the Earth, specifically in North America, when we're over those boxes, we would turn the science instruments on. And then we just convert those ranges into usable data that a machine is closer to understanding. We look at latitudes and longitudes. We take that and we just turn that into basically Boolean logic. And then we can start designing our state machine. When you're in science mode, if you're in one of those boxes, we turn on the instrument. When you leave one of those boxes, you turn everything back off. That is the basics. That's all it is. It's a switch that gets flipped. We won't go too far down the design of this, but rarely is anything that simple. We're not going to cover this in depth, right? But this is actually on noscube.org. This is an example that I developed that basically this is all just for an example. This was all put together online. But you have to do things like tell the ground where you are, turn on the ancillary instruments. Do you need star trackers? What happens if the power's low? What happens if the power's high? What happens if somebody tells you to stop doing science? And the state machine rapidly gets bigger, right? So this is where dynamic testing with a full simulator is useful. So the point is, without that high fidelity sim or twin, how do you test your changes? Well, we can use these tactics, techniques, and procedures from matrices like Sparta to drive these. And very specifically, what we're going to look at today, really proud of this. Donnie and I worked really hard on this one. If you take the Sparta framework and you drill down, under spoofing, you can spoof sensor data, or in this case, it's really position, navigation, and timing. So let's do it. Let's do it live. Well, not live, but it could be, but I don't trust myself at the moment to get it right. Make sure we're running here. We are running. All right. Video's running. We got a few things going on here, and I'm going to talk through what's happening first, and then I'll orient everybody. Right now, I'm playing with the command sender window here. Just sending a no-op. You can see in the flight software it says it received the no-op. There's a delay before that gets back down to the ground. So right now, in this video, we're commanding a spacecraft. It's receiving telemetry from the ground. It's acting on it in real time. It's following its telemetry process and generating packets to go back down to the ground. Command counters are incrementing. And I'm looking at a very specific telemetry page here for a little application we call Manager. So basically, we're just going to configure the experiment we just talked about. We're going to measure moisture over the U.S. So we set the mode to science mode, and we enabled, you can see a little green in the bottom right, the CONUS config for the continental U.S. Once we start science mode, you can see a lot of stuff's going on. These are all that's that diagram I showed you. It's happening. It's turning on switches. It's getting to a known state so it can proceed safely. And it'll take a minute, but once it initializes, you can see that science initialize pops up on our telemetry. Now, if you didn't have all these handy little macros and telemetry, you would just see numbers, and that's very hard for operators to understand, like is a 0 or a 3 good or bad. So we basically alias all of these. So now we are ready for science. The satellite has the green light to perform science. It's just waiting to get over the U.S. Now you can kind of see by the boundary boxes, right? Like it's not a tight bound. It could be. You could do all the processing power you wanted or use some sort of a model or geospatial information to do this. But to keep it simple, we're just drawing kind of large square boxes, and we've given the satellite a green light. So let's see here. We have some time ticks, and it's worth saying that this flight software window, obviously you wouldn't see. There are ways in the telemetry to print out event messages, but it's kind of nice to have this little console to give us the window into what's actually happening. Also, the speed right now, we're running about 2 times real speed. Oh, hey, something's happening. Science mode. Satellite's telling us we're entering the continental U.S., and we are. You can see in the bottom right in the telemetry, it says we're doing science over CONUS. The science pass counter has incremented, so we have an idea of how many times we've done science. And it's going to start actually reading data. Other things that are going to happen right now is, if you think about state machines, you want to try to make something that's really robust. So if you, in this case, for everything that's happening, if you picture a house with a handful of doors, you're standing outside the house and you shut all the doors because you don't know which one you're going to use. When the satellite stumbles into one of these boxes, it opens a door. So now you're standing inside the house, one door's open, you look around, you touch all the doors and you shut them all because you don't know which one you're going to be leaving out of. Doing the logic like this in the state machine simplifies the state machine, believe it or not, but it complicates the Boolean logic a little bit. But the point is, if somebody can manipulate something at a time that you do not expect, it's hard to tell what your state machine is going to do. If you're always operating under the assumption that you're very cleanly going to enter the U.S., and then leave the U.S. but be near the U.S., is your power going to be right? Does that affect your attitude, your battery power? One of the things we have here pulled up right now is the GPS. And so these are coming from our GPS simulator. We are emulating a Novatel OEM 615. They let us do that as part of FTF1 and open source the model. It is receiving dynamics data from 42. It's generating the actual GPS string in a NEMA format. Flight software pulls that string from the hardware model, and the hardware model says, this is your GPS data. Flight software extracts that, and this is what the GPS data looks like, just screaming by in debug mode in real time. So this is everything coming from the dynamic simulator into the hardware model, and then getting shipped out to flight software. And it's going, I don't even know how many times a second. And we're running at 2 times real speed. So this is also EPS data. Not only are we doing all of the GPS, but the EPS itself is really hard to see, but there's a voltage in the bottom that's counting down very slowly. It's like 21.14 volts, 21.13 volts. So we're using power because the science instrument is on, even though we're in sunlight. We've designed the mission this way. So there's a lot of really cool stuff that's happening here. So if you think back to the diagram that I just blew past that had 1,000 boxes on it, one of those is low power. And it's a nominal operation that your satellite doing science is going to have low power. And when you have low power, you need to turn the switches off. It's not a failure state, it's an expected state. And then when you get back up to normal science power levels, you can start doing science again. So you can bake in layers and layers of automation and test it on a simulator like this. Let's see here. Filter counted. Somewhere we're coming over, I don't know. Starting over Tennessee. We're heading to the northeast. We're going to keep going that way for a minute here. But the important thing for this demo, for what we're really doing, is that we have a GPS hardware model. It's receiving sensor data from its antenna, which is our dynamic data. It's converting that to what the manufacturer actually says that hardware would spit out based on that information. So if you go to that GPS and you say, give me the GPGGA or whatever string, we get that format. Flight software processes that format. We extract the latitude and longitude. We ship it down to the ground so the ground can also see the latitude and longitude of what's going on. And the system goes on its happy way. We see I just changed back to the manager telemetry in the top right. And we're still in science mode. We're still doing science over the US. Science pass count is 1. We started at 0. There's some other cool logic in here. It looks like I turned on Hawaii at some point. It keeps track of anomalous reboots. You want to talk about error correction or mitigation. A lot of missions, especially like lower budget CubeSats, they're like, what are you going to do if you get locked up? And the answer is, we reboot every 24 hours. Awesome. What if you're talking to it during those 24 hours? Doesn't matter, reboots anyways. And that is very maddening when that happens because I've done it. I'm like, I didn't design that part, but like, you're like, all right, we're going to talk to it. And you say, hello, satellite, and it says, I'm rebooting, I don't have time for this. All right, so, but that's not an invalid way of clearing faults, right? I mean, how many times do you power cycle the router at your home if it gets locked up? Like, you do it. But if you think about servers and deployed infrastructure, you're probably not going to just reboot it every 24 hours if you've got users, right? It's more of an as-needed basis. So we're about to leave the northeast here. We can see our little satellites doing some spin moves down here. I don't remember what I told the attitude system to do or why it's spinning. But you can upload different models. It comes preloaded with CubeSats. I think the ISS. There's also one of those big stone, what do they call it? What are the stone head guys that I don't know why it's in there, but you can fly a big floating head through space if you so choose. It's probably my favorite. So let's see here. Let's give it just a minute. Oh, perfect. Good timing. So we left the continental US. Let's see what happens in our telemetry. Our telemetry here says, hey, by the way, science is over. We're still in science mode, but we've left the region of interest. We're going to start flipping all these switches and turning stuff off. As a result, our power consumption goes down. And then, as you can see, We're still in the sunlight of the map. You can see the sunlight in the eclipse. But if we were in the eclipse, it would actually go down faster. So we're even modeling power whether or not we're in sunlight here. And let's see what I'm doing. Now this is the magic. I'm going to pause it for a second. The important thing about this demo is you can do this demo and you can modify flight software. You could go in and you could take your operating system flight software and say, when I send you a special command, pretend you're somewhere else. But you've modified the thing you're testing. That's not the best way to do this. You don't want the flight software to know that you're even testing it. You don't want to make any modifications. You want what you fly to be the exact same thing that you've tested on the ground. Now, I grant you that for this demo, this is just compiled for Linux. It's not cross-compiled. We are working on an open source model so we can ship NOSCube and you can have an open source actual like flight processor to run it on. So that's coming. And normally in a lot of our sims, we do that. It's just not models we can share publicly for ITAR and other reasons. So what I'm saying though is we want to test this, but we don't want to modify the software. We don't want to modify the virtual hardware. We want to modify the data coming into the virtual hardware to see how the entire embedded system reacts. So in my command window down here that I've got highlighted blue, we have this really cool tool that we call the command bus. Now, or sim command bus bridge. It's cut off. But even though it's in the command sender, I don't want you to think that it's following the normal uplink path to the satellite. It's not true. On the back end, we are taking that around in the back door, and we are feeding that to the simulator. So in this example, right here, we're able to scroll down, and we're going to pull up I'm going to pull a little wider so we can read it first. But we're actually going to pull up the command bus for the Novotel, that is our GPS, and we're going to spoof the signal coming into the GPS. The satellite says, cool, I'm over the US. It's not over the US. It's spoofed. It's over the ocean. But are your embedded systems smart enough to know? Is your satellite smart enough to know that if you leave the US, 5 minutes later, are you back in the US if it takes 90 minutes to go around the Earth? Is the system you designed that somebody's poking at, that they're trying to get into, can it handle these types of attacks? What if we talked about the logic in the state machine? What if you didn't design it in a way that it turned everything off safely, and somebody spoofed this and left it on when you went into Eclipse? Are you going to drain your batteries? Or are you just assuming that you would never do science in Eclipse anyway, so you're not going to check the power level? So this is really cool. I'm really proud of Donnie and mine's work on this. This is a complete spoof at the sensor level, and the entire system is reacting to this. Despite we can see on the map where it is. We know where it is, but the satellite doesn't know. The Novotel hardware doesn't know. And as a result, the flight software doesn't know. This is an innocuous example. This is just a sensor reading moisture. This is not something worse, I'll put it like that, right? But this extends not just to satellites, but all embedded systems. Think about Stuxnet. In this case, we're telling the system it's doing something. In the Stuxnet's case, it lied to us and told us what it was doing. But it's not impossible. It's not impossible. And a lot of your embedded systems and satellites work off, they work off what? They work off security through obscurity, right? So there are real examples out there of similar situations happening. So in summary, we just did something cool. We just spoofed GPS sensor data. We just watched the satellite turn on where it should not be turning on. And then actually, if you sit there, I toggle a few more times and just turn it on and off for fun. And a really good example is when you saw all those commands going by, those stored commands, they come through and there's like a 1 second pause. So you can turn it on, and every second it turns on a switch, checks something for safety, turns on a switch. What if you just start spamming that spoof command? Things will get turned on, they're going to get turned off, they might be left on, I don't know. It depends on the order that it runs, because some of these can run more than one command sequence at a time. It was cool. So we talked about embedded systems, we covered the use of digital twins for embedded systems, not just space, even though I have a space example. And we used an open source platform to demonstrate GPS spoofing at the sensor level, not modifying hardware or the flight software. And that's all I've got. Thank you very much. Does anybody have any questions? All right. Thank you.